Please welcome Vitalik Buterin.
Okay, so basically, this is a bit of a ow. Okay, so what I'm planning on talking about today is kind of one small part of Ethereum's scalability research that and Ethereum's proof of stake research that we have been making a lot of progress on recently, right? So a lot of people who have been following Ethereum's proof of stake progress probably know about Casper FFG, Casper the friendly finality gadget, which is probably a proof of stake consensus algorithm that's inspired by a combination of ideas from traditional proof of stake and ideas from traditional Byzantine fault tolerance theory that gives a lot of the same really nice properties that you can get from traditional consensus. So safety under asynchrony being a big one, but at the same time has a lot more efficiency properties and can scale up to a very large number of validator nodes, right? So we're talking about having enough scalability so that you can have blocks finalized quickly, and at the same time, you can have a proof of stake blockchain that has tens of thousands, hundreds of thousands, potentially more than 1 million people participating as proof of stake validators. So CBC Casper is this kind of different school of proof of stake research that was originally invented and kind of developed by Vlad Zamfir. And a proof of stake is a kind of very different school of consensus from the one that most traditional consensus algorithms are based on, right? So the main theme of CBC is this idea that validators choose kind of some chain which is canonical based on an estimator. So this basically is kind of fancy language that says validators follow some fork choice rule. So fork choice rules are just a rule that says if you have a bunch of blocks, which blocks are part of the chain that actually is the correct chain, which blocks are part of the chain that everyone kind of actually listens to and follows, right? So in proof of work, for example, the fork choice rule is fairly simple. We talk about the longest chain rule. And in proof of stake, but there are other fork choice rules as well. So with CBC Casper, basically validators are following some fork choice rule that we can define. And when a validator follows a fork choice rule, they build a block. Then as if everything is working correctly, all of the validators are kind of reinforcing the dominance of some particular chain. And so as more and more validators build on some chain, that chain gets kind of stronger and stronger. And at some points, you can mathematically prove that the chain becomes kind of locked on some particular block, right? So once enough validators build on some particular block enough times, you get to the point where it's just not possible for validators to build on some other chain without acting in some way that's kind of provably malicious, right? Without acting in some way where anyone else can prove that some validator acted incorrectly and use that information to penalize them. So there's a lot of differences between CBC Casper and what Ethereum is working on right now. Probably the biggest difference is this idea that finality is client-side. So if you follow traditional consensus algorithms at all, the idea is that you have some specific algorithm that everyone needs to follow and some specific algorithm that everyone uses for deciding when some block is accepted as final, right? So you wait until you get like messages from 2/3 of all the participants and you wait for another round of that. If you see both of those messages, then you accept that this block is final. And there is this kind of one set of rules for when some block is finalized, and it depends on some specific fraction of validators, usually 2/3 of validators sending messages. So it kind of prescribes a lot about what validators are supposed to wait for, what the assumptions are, what validators are supposed to expect. And Casper FFG is kind of based on a lot of those principles. And the reason why we want, I'll talk about the reason why we went with Casper FFG a bit later, but a lot of it just has to do with its relative simplicity of implementation. But with Casper CBC, the interesting thing, there's a lot of interesting things about it, right? Which mean that even though it might take a slightly more complexity to implement and it takes more time to kind of develop, once the logic is all figured out, there's a lot of ways in which it's actually simpler to reason about, right? So the LMD Ghost fork choice rule, this is the thing that Casper FFG and Casper CBC are both building on top of. And it's an adaptation of Ghost, which is the greedy heaviest observed subtree, which is a fork choice rule that was originally developed in the context of proof of work back in 2013. And the problem that Ghost is trying to solve is basically what happens if new blocks come in more frequently than the network latency. So what happens if new blocks come in so quickly that it's just not even physically possible for every block to point to the previous block, right? So in the kind of traditional blockchains, we talk about the longest chain, and we talk about everybody's blocks kind of making the longest chain even longer, but what if blocks happen so fast that you just can't have, even if everybody's honest, you can't have everybody's blocks fit into a chain? And the way that Ghost works is that instead of trying to look for whose chain is longer, you kind of start at the root of a tree and you sort of work your way up the tree. So you work your way up going from the oldest block to its children, to the children of its children. And at every step where you have a decision, you take into account all of the messages or all of the blocks that support either branch of the decision, and you figure out which one has the most support. So in some sense, it's kind of more efficient because, for example, in this particular case, right, if you look at, say, blocks A and B, well, blocks A and whoever built block A and whoever built block B, the ones on the blue ones, the ones on the right, they really both support block E. So really, the vote for A and the vote for B are also both votes for E. But if you look from a longest chain rule point of view, they only really count as one vote for E, right? So the idea basically is that in these cases where even honest validators are kind of imperfect and even honest validators are not able to make blocks that all are nicely arranged in a chain with each other, how do we make sure that if you have two validators or miners or whatever that vote for E, how do we actually count them as being two votes? So the idea with Ghosts is basically that you kind of start from Genesis and you walk up the tree. And every time there's a decision, you basically check, well, which side of the tree has more support. Now, what do we mean by support, right? So in a proof of work Ghost, generally just any block counts as support, right? So we just say, does the tree, let's say we're at the second block, right? So we're at the second block that has a 5. And we're trying to decide, do we take the top tree or do we take the bottom tree? Well, the bottom tree clearly has way more blocks supporting it, so we take the bottom tree. Then you move one more to the right. Do we take the top tree, the bottom tree, or the middle tree? Well, the middle tree has more blocks supporting it, so we take the middle tree, right? So you can see how this is still a way of determining which chain is kind of best supported by the consensus of all the nodes, but it's somewhat better because it's just better at taking into account the information that two blocks that are not part of the same chain can still be supporting the same thing. So when we talk about latest message-driven Ghost, we're talking about something a bit more specific, right? We're talking about a fork choice rule that works kind of this very similar way, except instead of just counting blocks, right? Instead of just counting all of the blocks that got produced, it only counts the most recent block created by each validator. So in this particular case, right, we're assuming this kind of architecture where time gets broken up into slots. During each slot, some validator has the ability to create a block. And, well, so here we're going to assume the 5 validators are A, B, C, D, and E. Well, so you have 5. In this particular case, we're going to look at, well, what are the most recent blocks created by each validator? So you have the most recent block created by A, the most recent one created by B, by C, by D, and by E, and I've covered them in blue, right? So then if you use Ghost, then if you need to decide which of the trees to pick, you kind of count up all of the blocks that directly or indirectly support or a part of one particular tree, right? So in this particular case, so let's say you have a bunch of blocks that get created like this. The branch at the very top has one latest message supporting it. The branch at the bottom has 4, so you pick the branch at the bottom. Then if you then kind of move to the right and look at the inside the branch at the bottom, you have another fork. Do you choose bottom, middle, or top? Bottom has one supporting, middle has two supporting, top has one supporting, so you pick the middle. So so you might want to ask, well, why do we want to use Ghost, right? Why do we want to use Ghost, and specifically, why do we want to use LMD Ghost? So there's a couple of kind of really nice properties that Ghost has. So one of them that I mentioned is that longest chain rules, so the kinds of fork truest rules that we use in traditional proof of work, that we use in traditional proof of stake, do not have the ability to take into account information that comes from frequent parallel attestations or frequent parallel messages, right? So if you have messages appearing more frequently in the network latency, then you're kind of not taking that information into account. But if you use Ghost, then you are taking that information into account. Now, another interesting thing about latest message-driven Ghost specifically is that a minority can never beat a majority regardless of how many messages they send. So for example, if you look at this image over here, right? So A, B, C, D, and E, we're going to assume are kind of 5 proof-of-stake validators that are participating in our proof-of-stake system. Well, so here we're assuming that B is kind of one attacker, right? So B is just kind of off on their own. They could be trying to break the network, or they could be just disconnected from the whole network. And B is just making a chain that only has B in it and nobody else. And then down at the bottom, we have A, C, D, and E. And A, C, D, and E are just kind of peacefully trying to extend the chain, right? So the key here is that no matter how many blocks B makes, because we're using LMD Ghost, and LMD Ghost only takes into account the one most recent message that any particular validator made, nothing that B can do can make the chain that B supports be longer than the chain that everyone else supports. And this is a very nice property, right? It's basically, now one of the reasons why it's a very nice property is because it allows us to make these stronger guarantees that say once enough messages have been sent, no matter who does what, unless a very large portion of validators do something wrong and do something wrong in such a way that we can prove it and we can penalize them, the chain at the top is never going to win. And in fact, even in this exact configuration, right? So if, let's say, these 10 blocks are the most recent, or these 11 blocks are the most recent 11 blocks that got created, we can actually prove that the first block A at the bottom, so the block A that's right at the left, is finalized, meaning there's just no way that anything any chain that does not contain that block can, in the long term, be the chain that everyone agrees on. Now, finality is not a property that proof of work has, right? So in proof of work, there could always be some other chain, and that other chain could always have more hash power, and someone could always just rent out a bunch of hardware and do a 51% attack, or potentially there could just be a lot of miners that are offline, and then they suddenly come online, and that block ends up winning, right? So in proof of work, you do not have this property that you don't have this concept of finality, because it's just always possible that whatever block is not part of the main chain right now becomes part of the main chain later if some miners that were offline come online. One of the really nice things about proof of stake is that you can have finality, right? So you can have this property that says that unless a large portion of validators do something that's kind of provably malicious, that allows us to penalize them and take away their money, the chain at the top is not going to win. And now, I'll probably stress that this is a property that Casper CBC and Casper FFG both have, and I'll talk about some of the interesting properties that Casper CBC has versus FFG a bit later, right? So how do we prove this? So we can look at the global view, right? So the global view basically says you have a block on the left and you have these 10 blocks on the right. But then from the global view, we know things about the views of each of the 4 individual validators that participated in the chain at the bottom. So we have one bad guy, which is B, and we have 4 good guys, which are A, C, D, and E. Well, let's look at what we know about A. So the most recent block that A made is the green block at the top left, right? And so what do we know? Well, because A made that block, and because that block contains pointers to these other blocks, we know that A knows that the four out of 5 validators have made their most recent messages on the bottom chain. Now let's look at what C knows. Well, the most recent block that C knows is the green block at the top right, right? And so now we know that C knows that the 4 messages that the most recent messages that A, B, C, or that A, C, D, and E made are all at the bottom, are all part of the bottom chain. We also know that D knows that the most recent messages that A, C, D, and E made are all in the bottom chain. And we know that E knows that the most recent messages that A, C, D, and E made are all part of the bottom chain, right? So because after kind of 2 rounds of messaging, you have this kind of interesting kind of almost common knowledge property, right? That not only do you know that the most recent messages that most of the validators made are supporting the chain at the bottom and not the chain at the top, but you also know that almost all the validators know that, which is, and now you might want to ask, well, why do we care that we know that everyone knows? So the answer basically is that this is needed to prove finality, right? So the claim here basically is that we know that unless at least 2 validators make blocks that are in violation of the protocol rules, that no validator except B can build a block on the top chain. So just from the information that we can infer from the block structure, so just from the information that we can kind of figure out for ourselves, only knowing, just seeing the chain at the top, we can discover that it is illegal for A, C, D, and E to build on the top chain. Now, you might ask, well, why is that? And the answer is that well, let's look at A. We know that A knows that the bottom chain has support from 4 out of 5 validators. And so for A to move to the top chain, like basically there would have to have been at least 2 other validators that moved to the top chain already. So if, for example, A and C just illegally move to the top chain, then the latest message fortress rule might support the top chain, and then B could move over. Or sorry, and then A could move over. But if that doesn't happen, then A can't legally move over. Well, let's look at C. We know that C knows that 4 out of 5 validators support the bottom chain. So therefore, we know that C has no way to legally move over. And we know that D has no way to legally move over. And we know that E has no way to legally move over. And so none of the validators can legally jump over to the top chain unless at least 2 other validators do that first. And whoever jumps first, well, we know that they made a block illegally, and so we can penalize them. So this is kind of what we mean by economic finality, right? The block A in the bottom chain is kind of locked in such a way that we know that it's just not possible for the top chain to ever win unless at least 2 validators are willing to just sacrifice themselves and make blocks that just clearly violate the protocol rules. So more generally, there's a heuristic that's called the 2-round clique oracle, which basically says that if there exists a 1/2 plus p size subset of validators that all support the same chain with 2 consecutive rounds of messaging, then the earliest of the blocks that's signed is finalized with safety margin p, which basically means that p of the validators would need to do something illegal in order for it to be possible for some other chain to win. So in this particular case, right, we have 4 out of 5 validators that built on the bottom chain twice. And so P in this case would, well, 4 out of 5, that's 0.8. So P in this case is 0.3. And in this particular case, guess what? We need 2 validators to move over to the top chain illegally. So that's basically, well, we can't have exactly 0.3 because there's only 5 validators, so we have to round up to 0.4, right? So the math checks out. Now, this is sufficient but not necessary for finality. So the 2-round clique oracle is only one of the conditions under which you have the safety margin. And there's plenty of other conditions under which you have the safety margin as well, but most of them are probably exponentially difficult to compute. So, but fortunately, you know, we don't need to compute all possible cases in which we have safety. As long as we have some kind of good enough heuristics, then clients can figure out most of the time when blocks are finalized enough. So cool things about CBC Casper, right? So basically there's, first of all, so this is kind of the question that you might want to ask is, well, we already have Casper FFG, and Casper FFG is what Ethereum 2.0 is going to kind of the spec has, and what everyone is building, and what everyone is working toward at this point. But there is this kind of longer term idea that many people have that at some point CBC makes sense as something to switch over to. Well, why do we want to do that, right? So first of all, with CBC, different clients have the ability to privately choose different safety margins at which they consider a block finalized. So if one client has the opinion that there's no way that more than 10% of validators are going to do something wrong, then that client can accept finality a bit faster. If some other client has the opinion that, well, maybe all the way up to 50% of clients might do, or of validators might do something wrong, then that client is going to wait a lot longer until it accepts a block as being finalized. So also, if some client believes that some nodes are permanently offline, so let's say, for example, the apocalypse happens and 70% of all the nodes just disappear, and because we know that it's an apocalypse and we know that those nodes are never coming back, then any particular user that privately knows this fact, so if any user privately knows that these 70% of people are offline and they're never coming back, they can use that information to detect finality, right? So a user that does not have this information will see that, oh, there's a chain and only 30% of validators are supporting the chain, right? Now 30% is less than 50%, so the 2-round Greek oracle never gets triggered, and so a user without this information never kind of experiences finality. But if you as a user privately know that these 70% are permanently offline, you can just you can just take into account the fact that they don't exist, and instead of looking at the entire validator set, you can look at only the 30% that you know are going to continue to be online. And this is really nice because then basically you, with this private knowledge, can get this private idea that this block is finalized under your extra assumption. This is something that you just cannot do with FFG because FFG forces everyone to kind of agree on what the threshold is and who's part of the threshold. CBC does not. You get some amount of safety with 50% plus epsilon off online. So with FFG, if more than 2/3 are online, you get a lot of security. If less than 2/3 are online, blocks never get finalized. With CBC, even if 55% are online, you still get that kind of 5% security margin. And CBC is really nice because you can kind of bolt it onto existing systems very easily. Now, one of the nice things about FFG, and one of the reasons why we did Casper FFG, is that FFG is very easy to kind of bolt onto consensus algorithms very easily. Well, guess what? CBC is even easier. So why upgrade to CBC? So first of all, there's a kind of inherent ugliness in how FFG works, basically because of how FFG, the problem with FFG is that the mechanism for finalizing blocks and the mechanism for agreeing on blocks in the short term are kind of disjoint. You can kind of make them both be proof of stake, but really they're two different mechanisms. And intuitively, you can think of it as kind of there's being this tension between these two mechanisms, and what this tension could lead to is it could lead to cases where it becomes harder to finalize blocks, right? So if you get really, really unlucky, and if the network kind of becomes structured in the worst possible way, then there is a risk that attackers can kind of force the network to bounce back and forth between two chains for some period of time and really delay finality. CBC just completely bypasses most of these issues because with CBC, you don't really need, instead of short-term kind of agreement on which blocks we're going toward and consensus and blocks being finalized being two different processes, one process kind of organically arises out of the other process. So why haven't we upgraded to CBC yet, right? So basically the main issue here is efficiency, right? So in CBC, there's one validity condition, and the validity condition just defines when a block is valid. So the validity condition says if a block is created with parent P and its latest messages in the set of messages included in B and its ancestors is M, then B is valid if P is the output of executing the LMD Ghost fork choice rule with M as the latest messages. Now, this is like fairly complicated tech babble, but in English what this means is that a block is valid if, given all of the evidence that B knows about, B actually is the correct block that should have been created. So mathematically, you can kind of get how it feels really nice and simple. The problem is that computationally, this takes a long time to actually check, right? If actually running the LMD Ghost fork choice rule on every block is not easy. So there was this kind of computational issue. CBC also has a swashing condition. So swashing condition basically means if a validator contradicts themselves. So they do one thing which is valid by itself and a second thing which is valid by itself, but those two things are not valid together. So intuitively you can think of it as they do one thing that's based on some piece of evidence, and then they do some other thing which looks like they kind of pretends to forget that they ever knew that that evidence existed. Then that's something where you can catch someone doing it and you can say, hey, look, here's cryptographically signed evidence that you did these two things that contradict each other, and we can use this as evidence to penalize you, right? So there's a swashing condition in CBC, and the implication basically is that if you make even one block that takes into account some piece of evidence, so some set of things that you know other people did, then all future blocks that you make after that also have to take that same evidence into account. So the beacon chain, so this is the Ethereum 2.0 chain as it exists today. There's a lot of challenges in actually implementing it, right? So one of them is that you have, in the worst case, you have potentially up to 4 million validators, right? So the current the numbers in the current spec suggest that you have, you need 32 ETH to become a validator in the proof of stake mechanism. The total supply of ETH at this point is a bit over 100 million. Divide 100 million by 32, and you get 3 million validators in a bit. And each of them sending a message every 6 minutes. So we make this practical in two ways. One of them is this idea of kind of separation between blocks and attestations. So blocks are kind of part of the blockchain, and they are things that contain transactions. Blocks point to other blocks. And attestations are just signatures. They're just votes from a validator that says, this block looks good, I support it. The number of blocks is basically one every 6 seconds. The number of attestations is potentially many thousands every 6 seconds. So we have this kind of separation between blocks and attestations. Attestations contribute to the LMD Ghost fork choice rule. Blocks contribute to the kind of blockchain DAG structure. And we separate the two, right? So this makes it more efficient. We also have a BLS signature aggregation, which is a cryptographic technology that makes it much more space efficient and much more computation efficient to have many signatures from a very large number of validators. But you only get many of the efficiency gains if these messages are all signing the same thing. And so we need all these messages to be signing the same thing, right? But CBC Casper requires each message from a validator to be somehow referring to the previous messages signed by that validator. So there's a couple of solutions to this, right? So one of them basically is that instead of requiring a validator to point to the previous thing that they said, we require a validator to point to a Merkle tree containing the previous thing that everyone said. So what this basically means is that even though you still get this property that the validators are ultimately kind of attesting to the same information, now you have all the validators signing the same message, which makes BLS aggregation practical. Another one is that computing the LMD Ghost fork choice rule takes a huge amount of time. So one solution, there are kind of a lot of different ways to optimize this. One solution that we came up with recently is adjusting the fork choice to something we call Bitwise Ghost. So Bitwise Ghost basically says if a block has more than 2 children, then instead of looking at it as a block that has 3 children, you kind of separate out the graph even more and you agree on the hash of the next block bit by bit. Now, every bit, there's only two possibilities. And so you basically turn one block with 3 children into a block with 2 children, where one of those children itself has 2 children. This is really nice because basically, instead of verifying the LMD Ghost fortress rule itself, you're instead verifying a kind of much simpler mathematical claim, which basically says, out of everyone who voted at one particular height, at least half of them stay until the next height. And so this makes kind of much more mathematically simple to verify whether or not a block actually is valid, which makes Ghost much more efficient in a bunch of ways. So what does this mean, right? So in general, this is an example of how this kind of fairly unique and different approach to a proof-of-stake consensus can be kind of bolted onto existing systems. So you can think of Casper CBC as something that you can just kind of bolt onto existing proof-of-stake chains, like basically any kind of chain that's willing to switch to something like LMD Ghost as a fork choice rule. It's also usable by basically any proof-of-stake chain. With some of these latest improvements, it basically means that there's a lot of progress at dealing with scalability issues and potential faster deployment in Ethereum, right? So before we were thinking of Casper CBC as being a kind of very far off, like 5 year off thing that we would do for Ethereum 3.0. At this point, it looks like it's in the cards for like Ethereum 2.x. So it's a significant improvement. I mean, there's a lot of kind of significant technical improvements in here that will lead to the fork choice rule becoming, and the proof-of-stake consensus mechanism in general being cleaner, being simpler, having kind of fewer moving parts, probably having simpler economic analysis in a bunch of ways, which is all really nice, right? So now of course, in the short term, there's still quite a lot of work to do before something like CBC can actually be turned into an algorithm that you can use in something like the Ethereum 2.0 beacon chain. And so this isn't something that would be possible to just kind of throw out FFG entirely and start developing tomorrow. But at the same time, it's closer, right? So in the short term, one of the other really nice things about this is that when we end up switching to something like CBC at some point later, most of the work that we've done right now actually is not wasted, right? So even if you look at the current beacon chain spec with Casper FFG, the actual kind of difference in code between the two is not extremely large. There's a bunch of things that you would have to change, but it's not like you have to just kind of throw out the entire design and make a totally different design. This is something where you can take the code that we're using for Casper FFG, and it's really just removing a few things, adding a few other things, changing the structure of what validators are signing, and you can kind of switch it over, right? So this is nice. Now, it's also important to note that this is, another nice kind of thing about all of this is that because of the way the Ethereum 2.0 beacon chain is being built, it's the consensus and the sharding are done kind of almost separately. And so anything that happens over here basically has no bearing on what the sharding architecture will look like, right? So sharding will basically, this does not include any kind of improvements in how at least at this point, in how sharding can be done. Now, Vlad has like a lot of very different and more radical ideas.
Thanks, Vitalik.
Mm-hmm.
I think we have time for like 4 or 5 questions, so you can pick and we'll go and get them.
Let's have some diversity. How about a question from someone in the back row? Yes.
Hi, Vitalik. How are you?
Good. How are you?
Good. I'm Colin Lowenberg from Dispatch Labs here in San Francisco. Thank you for coming and speaking.
Oh, well, thank you for coming.
One of the biggest concerns I have around Ethereum is the timeline. So can you give me a timeline?
So I would say in 2019, it's the main kind of bottlenecks are not on the research side, they're on the development side. So basically enough of the spec is kind of finished at this point that it really is, the critical path really is the development slog more than what we're doing. And so the people that can kind of give the most credible answers are not me, it's the actual client developers. Now, from my understanding is that the development teams have been promising test nets in the spring of this year. And I mean, if test nets go well, then I mean, mainnet, at least for the earlier stages of Casper, can come fairly soon, but you know, there's still a lot of unknowns, right? So if you look at spring 2019, and then for example, if you want to use Ethereum 1.0 as a benchmark, then in Ethereum 1.0, the time between the kind of last spec freeze testnet and the launch was 4.5 months. Here could be less, could be more, but that's like one way that you can guess. So a lot of uncertainty, but but if you want to kind of get more idea and more uncertainty, I'd encourage you to kind of keep on following the development process.
Thank you.
Mm-hmm. Yes. Yeah. So.
A lot has happened in 2018. So we saw a lot of the prices of the cryptocurrency are skyrocketing, and we also saw them fall to the rock bottom. Mm-hmm. So I mean, you know, Shakespeare said, "This violent delights leads to violent end." So my question is, what's your take on that, and how do we avoid that the violent delights that we're having right now turn into violent ends later? Because a lot of academians are actually thinking that, you know, the short-term profit seekers are making the market extremely unstable. So I would like to hear your perspective on that.
So I guess like what kind of like violent device are we concerned about here?
Well, I mean, like just in general. Yeah, I mean, it shouldn't it be like kind of obvious, like, you know, the violent delights is like a lot of people are making money like in this. So I talked about short-term profit.
I guess I would say that like unfortunately, you know, it's 2019 and it's kind of well into prices dropping quite a bit, which means that the community has already kind of suffered a lot of the result of the instability, and so it's unavoidable because it's in the past. In the future, I mean, even forgetting prices, my opinion about kind of the next stage of the crypto space has always been at this point that we just need applications and we need adoption. And when you want to ask why don't we have applications and why don't we have adoption, like when I tend to talk to mainstream enterprises that are looking at adopting the technology, one of the things that they very frequently reply back as to why they haven't done anything yet is the scalability issue. And one of the ways in which the scalability issue will be resolved is through things like sharding, for example, which is kind of dependent on a lot of the beacon chain work that some of which I talked about here. So if the tech gets developed, then we can see real stuff being done. If the tech does not get developed, then all we can do is speculate and yell at each other on Twitter. So, as a community, it's our choice. So if anyone wants to help the Ethereum research and development efforts, you're very welcome to, and come to our GitHub. Yes. Sure. Mm-hmm.
Hi, my name is Joelle Wright. My question is, what is Ethereum doing aside from ETH Denver and hackathons to ensure scalability and developer engagement? Are you guys looking to get into communities, on campuses? How can this become a community where everyone can engage to ensure that scalability is in place?
Sure. So ETH Global and the hackathons have definitely done a lot in a lot of places, but they're also, but it's definitely not the only kind of way that we want people to be able to engage. In terms of kind of large scale things that can attract fairly large numbers of people, like we've probably done a bit less of that so far because, like, for example, on the academic side, we tend to kind of focus on partnerships with like existing crypto-related and crypto-adjacent research institutions. And I know there are kind of student-led efforts and things and kind of grassroots things happening in a lot of places as well, but we have engaged with them less so far. We definitely want to find ways to change that. Another thing is that there's a lot of different things for people to do in the space, and one thing that we've been trying to work on improving is just communicating better what the challenges are and what kinds of things people could be working on. So, like for example, right now we have grants, but that can reach a limited number of people, and also that's in a lot of cases people don't even know like what kinds of things exist. But then there's also things that different projects in the Ethereum space are looking for. So that those are things we're trying to figure out how to support. I know we're looking at like things like doing better education materials and better translations. So like for example, one of the grants that we gave last year was to a project called cryptoeconomics.study, which is trying to create a kind of online course that gets people learning the ropes of how all of the different crypto tech works so they can start contributing. So looking forward to that coming out.
Perfect. I have a Facebook group if anyone's interested, Hackathon Hackers Cryptocurrency, and I'd love to have anyone who's interested in engaging developers. CoinList is working with helping us as well, but it would be an opportune situation. Hackathon Hackers Cryptocurrency, and I'd love for anyone to join so we can help Ethereum and all of the other cryptos build.
It's kind of about your story with World of Warcraft, actually. So I'm working on a gaming blockchain project myself, and just kind of let's throw the World of Warcraft example out here for I guess people that. I mean, do you want to do that, or my follow-up question is with that? Yeah.
What's your question?
Well, okay. So with the rise of NFTs, right? Essentially, when you didn't like that particular game, you now own the assets essentially to go somewhere else or liquidate or whatever. So you have essentially option to take ownership in the game, right?
Yeah.
But what hasn't been solved though is the data that's been used to make that balanced decision. Like a lot of the data will be off chain for quite some time to come. So what do you think? In that particular problem where you have off-chain and on-chain data in a game, how do you, what would that new game platform look like, I guess, on the blockchain, given that consideration of off-chain and on-chain data?
And there's a lot of different ways to combine together games with blockchains. So for example, you could just use something like plasma chains as a way of storing game assets, and then use the main chain for moving assets in between different games and interoperability. You could try to design the entire game on top of a blockchain in some cases, I don't know, something like some kind of virtual reality that kind of heavily involves having and using assets might make sense for something like that. I feel like there's a lot of models. I mean, I'm not the best expert in understanding what exactly the details of what that sort of thing would look like. So, but in general, I'm happy that there's a lot of different game companies that are interested in it, and I hope that we'll see a lot of different models get tried out, and we'll see which ones make sense. How about a question about Casper? Go.
Hi. I hope this qualifies, but is CBC Casper being designed with any transaction throughput goals in mind, or is it just going to be what?
So I know there's a lot of misconceptions here because there's a lot of honestly bad crypto projects that try to claim, oh, because we use fancy BFT, we can do 5,000 transactions a second, and proof of work can only do 15. there's a lot of horrible misconceptions inside of that, because the purpose of a consensus algorithm is not to make a blockchain fast. The purpose of a consensus algorithm is to keep a blockchain safe. So with the reason why things like proof of work can process relatively few transactions is because with the way proof of work works, it becomes unsafe if computers spend more than maybe 10% of the time at mining and verifying blocks. Whereas things like, for example, Bitcoin NG or things like the various forms of proof of stake could potentially be safe if you go higher than 10%. But the difference is still very small. So a lot of the time when a blockchain project claims we can do 3,500 TPS because we have a different algorithm, what we really mean is we are a centralized pile of trash that only works because we have 7 nodes running the entire thing. Now, the only way that you can get out of that, now there are legitimate, good ways of making a blockchain fast, and I would argue that the main good candidates are basically layer 1 scalability through sharding and layer 2 scalability through things like channels, plasma, and lightning networks, and ZK rollup. So the main difference between, real difference between the properties that different kinds of consensus algorithms can provide to you, one is not bandwidth but latency, so how quickly you can get finality. So in this case, we can go down from needing to wait 1 minute, say 1 minute to get a medium degree of safety, to needing to wait 6 seconds to get a medium degree of safety. And from needing to not having a concept of finality to being able to get finality in about 12 minutes. You can also, that's basically the two properties are the level of safety, so how difficult it is to either censor the chain or make blocks revert, and how long it takes for blocks to become safe. And those are really the two things that we're kind of thrusting to improve as much as possible with all these improvements on Casper. Still a question on Casper? Okay. Mm-hmm.
Very much enjoyed your response to the last question, but it does prompt me to ask one alternative which does claim high transactions per second, which, in my view at least, is not at all a pile of trash, is David Chaum's Elixir. I wonder if you have any comments on that contention.
So most of the time, basically, if you have a high TPS, then either you're sharded or you rely on a small number of nodes where each of those nodes needs to process a huge number of transactions. And if you have a very small number of nodes, then you have a kind of centralization problem, and so you need some kind of structure for kind of picking who those nodes are, and because you really need to pick trustworthy ones, and you need a structure for kind of picking who they are, managing them, kind of policing them. And that's something that I know there has been done work on. I personally am not satisfied with any of the algorithms I know about, but I honestly don't know about the specific approach that's being used in Elixir, and it's very possible they have something really cool. We'll see. And well, in that case, I look forward to Elixir publishing the specification of how its protocol works as soon as possible, so we can verify and enjoy its glory.
Hey, Vitalik, I'm sure people will have questions until this place kicks us out, but how are you feeling? Do you want to do one more? Or
One more, as long as it's about Casper. Sure.
If you could, I guess, send yourself some information back in time to when you were starting to develop Casper, what would be the one piece of information that you would send back?
Probably I would just cheat and say the current spec, the spec, but the problem is, well, the really nice thing about both FFG and CBC is that they are they rely on kind of very simple insights. right? So like the reason why I was unhappy, the reason why I'm unhappy with kind of the school of traditional BFT consensus, like as done with like PBFT and all these algorithms in the 1980s, is that they're just insanely complicated. And FFG, for example, just does a very good job of just, at least in my opinion, like definitely biased opinion, is that it does a good job of kind of distilling what is the core principle that makes safe under asynchrony consensus even possible. And it kind of, in my view, pretty elegantly sort of merges it into a chain-based structure, and it just makes those two things work together. And CBC does a similar thing, but it does it in this kind of very different way that doesn't even technically, that's like really even algorithmically substantially different from how traditional consensus works. Right, so before I came up with Casper FFG, I know I definitely spent kind of 2 years wondering how traditional safe under asynchrony BFT consensus is even possible, and just like not having that insight is something that just delayed us for a while. But then having the insight, it's like, and especially having it in this particular format, it's not especially difficult. So that would probably be the answer. Okay.
Thank you.